What if I told you the universe might be alive, not in the poetic sense, but literally conscious, watching us from the fabric of space itself? This isn't fantasy. Some scientists argue that dark matter could be an ancient intelligence, while black holes might be portals to realms beyond our comprehension, and that's just the beginning. Today, we're diving into cosmic theories so radical, they rewrite the rules of reality. From time running backward in parallel universes to galaxies evolving like living organisms, these ideas don't just defy textbooks. They tear them apart. If you're ready to question everything you thought you knew about existence, you're in the right place. By the time we're done, the night sky will never look the same. Close your eyes for a moment and picture this: a vast, shimmering cosmic film, stretching across the boundaries of space like the surface of a bubble. Now, what if everything you've ever seen, touched, or felt was nothing more than a flickering projection from that two-dimensional surface? That's the heart of the holographic universe theory, one of the most audacious ideas in modern physics. Here's the strangest part: it's not just philosophy. This concept emerged from studying black holes, where physicists discovered that all the information swallowed by these cosmic monsters isn't lost. Instead, it's somehow imprinted on their edges like a stamp pressed into soft wax. Take a black hole's event horizon, the point of no return. According to Leonard Susskind and other pioneers of this theory, the data of everything that falls in isn't destroyed. It gets encoded on the surface, pixel by pixel, in a kind of cosmic blueprint. Now, scale that up to the entire universe. What if the three-dimensional world we perceive, galaxies swirling, planets orbiting, even your own hands typing a message, is just a hologram, a grand illusion projected from a flat, distant boundary we can't see? This isn't just wild speculation. The math actually checks out. String theory suggests that the information needed to construct our entire reality could fit onto a two-dimensional surface at the universe's edge. Think of it like a movie stored on a disk, except instead of images on a screen, it's reality itself unfolding from data we can't perceive. Even more bizarre. If this theory holds, it means space as we know it might not be fundamental. It could be an emergent property, like steam rising from hot water, real, but built from something far more basic. Still, the biggest question lingers: why does this matter? Because if the holographic principle is true, it could bridge the greatest divide in physics, the clash between quantum mechanics and gravity. It might also mean that time, as we experience it, is part of the illusion. Maybe the past, present, and future are already written on that cosmic film, and we're just tracing our fingers along its surface. But here's the twist: what if time isn't even flowing the way we think? That's where things get even stranger. We all experience time as an unshakable fact, an arrow flying forward, dragging us from past to future. But what if that's nothing more than a convincing story our brains tell us? Einstein shattered the idea of absolute time over a century ago when he proved clocks tick slower near massive objects. But some modern theories take this even further. They suggest time might not exist at all, at least not in the way we feel it. The block universe theory paints reality as a four-dimensional sculpture where the past, present, and future are all equally real, frozen together like layers in ice. In this view, your birth, your life, and even your death already exist as fixed points in an unchanging structure. It's unsettling, but the math supports it. Even quantum experiments add fuel to the fire. Tiny particles seem to behave as if cause and effect can blur, as if time itself is flexible. So if time doesn't flow, why does it feel so real? The answer might lie inside our skulls. Some neuroscientists argue that consciousness stitches moments together like frames in a film, creating the illusion of motion. This throws philosophy into chaos. Does free will exist if the future is already set? Is change just a trick of perception? But here's where it gets truly mind-bending. If time is an illusion, what does that make the universe? Could it be something more than just a cold, mechanical clock? Some theorists dare to go even further, proposing that the cosmos isn't just running like a machine, but might actually be alive. And that leads us to our next revelation. What if the cosmos isn't just there, watching, calculating, maybe even thinking? The idea of a conscious universe sounds like science fiction, but some of the brightest minds in physics and neuroscience aren't dismissing it. Take Giulio Tononi's theory. Consciousness isn't just a fluke of biology, but a property that emerges when any system, whether a brain or a galaxy, integrates information in complex ways. So why wouldn't the universe, with its trillions of interconnected stars, black holes, and quantum entanglements, have its own kind of awareness? Imagine dark matter as the hidden architecture of a cosmic mind. Just as neurons fire silently beneath our skulls, these invisible particles could be forming the universe's equivalent of thoughts patterns we can't yet decipher. After all, dark matter doesn't just sit idly, it shapes galaxies like an unseen hand. Could its structure be more than gravitational scaffolding? Could it be the universe's way of processing itself? This isn't just poetic speculation. The mathematics of integrated information theory, the same framework used to study human consciousness, can, in principle, apply to the cosmos. If a single human brain can generate subjective experience, what might a network spanning billions of light-years produce? The implications are staggering. It would mean the universe isn't just a stage for life, it might be alive in its own inscrutable way. And that raises an eerie possibility. If the cosmos is conscious, does it notice us? Are we like fleeting sparks in a vast, dreaming mind? Some interpretations of quantum mechanics already suggest observation shapes reality, a concept that edges uncomfortably close to ancient spiritual ideas. Maybe the line between physics and metaphysics isn't as sharp as we thought. But if one universe can be conscious, what about others? That's where the multiverse crashes in. An infinite tapestry of realities, each with its own laws, its own version of awareness. Are they whispering to each other through black holes or entangled particles? The answers might lie not in our telescopes, but in the very fabric of existence itself. Picture this: you wake up one morning to find not one, but infinite versions of yourself staring back in the mirror. Some might be astronauts, others poets, or even strangers you barely recognize. This isn't just a wild dream, it could be the literal truth of reality. The multiverse theory suggests our universe is just one bubble in an endless cosmic foam, each with its own unique laws of physics, history, and even alternate use. And here's the kicker. This idea comes straight from the math guiding our best theories of reality. Inflation theory, which explains the rapid expansion of the early universe, predicts that space-time doesn't just stretch its splinters. Like bubbles forming in boiling water, new universes could constantly bud off, each with different fundamental forces. Some might have gravity so weak that stars never ignite. Others could be so dense they collapse instantly. Yet among this infinite variety, a handful of universes like ours would have just the right conditions for life. But how do we know if these other worlds exist? The answer might be written in the afterglow of the Big Bang itself. When universes collide, they could leave faint imprints, wrinkles in the cosmic microwave background, the oldest light in existence. Scientists are scanning this celestial fossil record for anomalies, hunting for bruises from a neighboring reality. Finding one would be like discovering a fingerprint on the edge of creation. Now, shift gears for a moment. Imagine if black holes weren't just colossal monsters lurking in galactic cores, but tiny specks smaller than an atom, hidden all around you. This isn't a horror movie premise. Some theories suggest the early universe may have birthed countless miniature black holes, some potentially evaporating in a flash, others persisting invisibly. If they exist, they'd warp space-time on microscopic scales, creating ghostly distortions no detector has yet caught. But here's the real twist. These tiny black holes might be our only window into extra dimensions. String theory proposes that hidden dimensions, curled up smaller than a quark, could exist alongside the three we know. A micro black hole's behavior might betray their presence, like a whisper echoing through unseen halls. Finding one could rewrite physics or even unlock the multiverse's deepest secrets. So where does that leave us, staring into a cosmic hall of mirrors where every question splits into infinite answers? Whether through colliding universes or vanishing black holes, the clues are out there, waiting in the dark. Forget everything you think you know about dark matter. What if we've been searching for the wrong thing all along? Instead of exotic, invisible particles, the missing mass of the universe could be hiding in plain sight as countless primordial black holes, tiny cosmic fossils left over from the Big Bang's first chaotic moments. Picture trillions of these atom-sized gravitational traps, each weighing as much as a mountain, scattered like invisible dust across the cosmos. Unlike their monstrous cousins at galactic centers, these relics wouldn't devour stars. They'd drift silently through space, bending light and warping time in subtle ripples we've only just begun to detect. The evidence, strange anomalies in gravitational lensing where distant starlight bends too much for the visible matter in its path. Some fast radio bursts, those cryptic energy flashes from deep space, could be the death cries of these ancient black holes evaporating in bursts of radiation. Even the way galaxies rotate faster than expected might not be due to dark matter's pull, but the collective gravity of countless micro-black holes woven into the cosmic fabric. But here's where it gets surreal. If these primordial black holes exist, they might be more than just dark matter candidates. According to string theory, their unfathomable density could puncture the fabric of space-time, creating bridges to higher dimensions. Think of them as cosmic thumbtacks pinning together layers of reality we can't perceive. A single one of these specks could contain a curled-up universe inside its event horizon, a hidden dimension where physics plays by entirely different rules. Now hold that thought, because dimensions might be the real wild card in this cosmic puzzle. We experience 3 of space and 1 of time, but what if there are more? Imagine space as a loaf of bread. We see the crust, but hidden inside could be countless folded layers, each with its own strange geometry. Some theories suggest gravity appears weak because it's leaking into these extra dimensions, diluted across realities we can't access. And those primordial black holes, they might be the only natural phenomenon violent enough to briefly tear the veil between these worlds. So why haven't we found them yet? Their size makes them ghosts in the machine, too small to spot directly, too massive to ignore. But new experiments are hunting their signatures: subtle gamma-ray flashes, distortions in gravitational waves, even heat signatures from hypothetical black hole stars powered by their energy. If we catch just one, it wouldn't just solve the dark matter riddle. It would prove our universe is far stranger and far more layered than we ever dared to dream. We're used to thinking of reality as having 3 straightforward dimensions: up and down, left and right, forward and backward, with time as the 4th. But what if space itself has secret passageways, tiny folded corridors too small for us to notice? String theory, one of the most promising attempts to unite quantum mechanics and gravity, insists that the universe actually operates in 10 or even 11 dimensions. The catch: the extra dimensions are coiled up tighter than a clenched fist, existing at scales so infinitesimal, even our most powerful microscopes can't glimpse them. Now here's where things get really interesting. These hidden dimensions aren't just abstract math, they might be the reason gravity feels so weak compared to other forces. Imagine a drop of ink spilled on a sheet of paper. In 2 dimensions, it stays contained, but if the paper had microscopic wrinkles, some of that ink could seep into unseen folds. Similarly, gravity's influence might be diluted because it's leaking into dimensions beyond our perception. That could explain why electromagnetism and nuclear forces dominate at small scales, while gravity barely seems to register until you're dealing with planets and stars. But the surprises don't stop there. Dark energy, the mysterious force accelerating the expansion of the universe, might also be tied to these hidden layers. Some theorists suggest it could be the pressure of higher dimensions exerting influence on our own, like invisible hands pressing against the fabric of space-time. If true, it would mean the fate of the cosmos isn't just governed by what we see, but by forces operating in realms we can't even imagine. So how do we test something this bizarre? Particle colliders like the Large Hadron Collider might hold the answer. If extra dimensions exist, smashing protons together at near light speeds could, for a fraction of a second, uncurl these hidden folds, creating tiny gravitational anomalies or even miniature black holes. No luck so far, but the hunt continues. Another clue might lurk in gravitational waves. Ripples in space-time from colliding black holes could carry subtle fingerprints of higher dimensions, stretching and compressing in ways that defy standard physics. Yet the most mind-bending implication of all, if these dimensions are real, the universe might not just have a hidden structure, it could remember things within it. Which brings us to an even deeper question. Is the cosmos keeping a record of everything that's ever happened? Let's shatter one of science's most stubborn assumptions, that cause always precedes effect. We take for granted that the past shapes the future, but quantum physics whispers a terrifying possibility. What if reality works backward too? This isn't science fiction. The idea of retrocausality suggests that future events can ripple into the past, like echoes traveling upstream through time. Think of a cosmic game of billiards where the final shot somehow changes how the balls were struck moments earlier. Experiments with entangled particles already hint at this. Quantum systems appear to decide their properties based on measurements made later. It's as if the universe is running on a hazy draft, editing itself on the fly. Some interpretations propose that particles send signals backward, tweaking their own histories to fit observed outcomes. But here's where it collides with something even wilder. If the future can touch the past, does free will exist at all? Or are choices illusions, their consequences already woven into the fabric of reality? This could explain why quantum particles seem to exist in multiple states at once. They're not just uncertain, but waiting for future context to lock them into place. Now tie this to the universe as computer idea. If reality processes information like a quantum hard drive, maybe time isn't linear data storage, it's a sprawling, self-correcting algorithm. Black holes might not just trap matter, they could be cosmic control plus Z buttons, rewriting spacetime's code to preserve consistency. Suddenly, the present isn't just shaped by the past, it's bartering with the future in a negotiation we can't perceive. So why haven't we noticed? Because our brains evolved to stitch events into orderly narratives. But deep down, the universe might be playing an infinite game of chess where every move adjusts the ones before it. The unsettling truth: you might not just be living your life, you could be debugging it. Here's the next segment, flowing naturally from the previous discussion while introducing fresh angles and maintaining engaging momentum. Time's arrow might not be as rigid as we believe, especially when the quantum world rewrites the rules. Picture flipping a coin and watching it spin in midair, only for the outcome to change after it lands. That's essentially what happens in retrocausality, where effects can ripple backward to alter their own causes. At the subatomic level, particles seem to defy linear time, adjusting their past behavior based on future observations. It's as if reality keeps editing its own script, blurring the line between what was and what will be. This isn't just a quirk of tiny particles, it could scale up to the cosmos itself. Some cosmologists speculate that the universe might have fine-tuned its initial conditions with its own future in mind. Think of the Big Bang not as a random explosion, but as a carefully set domino chain, one where the final domino somehow reaches back to nudge the first into place. If true, it would mean the universe didn't just happen to create life. It orchestrated it like a painter who starts with the finished portrait in mind. Now here's the existential twist. If the future can reshape the past, does free will even exist? Or are our choices mere echoes of events yet to come? Quantum mechanics doesn't give easy answers, but it forces us to confront a startling idea: time might not flow. It could simply be, with every moment eternally connected, like threads in a vast cosmic tapestry. And that raises an even bigger question. What if this isn't the universe's first or last performance? If time's boundaries are flexible, could reality be caught in an endless loop, cycling through creation and destruction? The stage is set for our next revelation, a cosmos that never truly begins or ends but breathes in an infinite rhythm. What if the Big Bang wasn't the beginning, just the latest reboot in an endless cosmic saga? The cyclic model throws out the idea of a one-time creation event, suggesting instead that universes rise and collapse in an eternal rhythm. Picture a cosmic heartbeat: expansion, contraction, rebirth, each cycle leaving faint echoes in the fabric of the next. This isn't just theoretical poetry. Ancient Hindu texts described something eerily similar: vast cosmic cycles called kalpas, where universes dissolve and reform like breath exhaled and inhaled by a divine force. Here's where physics gets provocative. If a previous universe collapsed before ours, its death throes might have left scars in gravitational waves, ripples in space-time we could detect. Imagine finding a fingerprint in the static of the cosmos, a whisper from a reality that existed before time as we know it began. Some researchers are already scouring data from observatories like LIGO, hunting for anomalies in these waves that could betray a cycle's turn. But the real curveball: the laws of physics themselves might not be eternal. With each new cycle, fundamental constants, the strength of gravity, the mass of electrons, could shift slightly, like a dial tweaked between experiments. That would mean our universe's delicate balance, perfect for life, isn't just luck. It's one iteration in a cosmic evolutionary process where only the fittest universes, those able to sustain complexity, persist across cycles. Think of it like a forest after a wildfire. The first regrowth is chaotic, but over repeated burns, ecosystems adapt. Similarly, universes might evolve, their physical laws honed over eons of collapse and rebirth. This flips the script on fine-tuning. Instead of asking why our universe is life-friendly, we'd ask how many tries it took to get here, yet the most haunting implication. If time is a loop, everything we are, every star, every thought, every moment has happened before and will happen again, but not identically. Each cycle carries variations, like a jazz improvisation on an infinite melody. So while the universe forgets, it also reinvents, and somewhere in that cosmic rhythm, we're both inevitable and utterly unique. Here's the next section of the script, seamlessly continuing the cosmic exploration while diving into the mind-bending idea that nature's laws might not be as constant as we think. We take the laws of physics for granted: gravity's pull, light's unshakable speed, the precise dance of particles that makes reality tick. But what if these constants aren't so constant after all? Imagine a universe where the rules themselves evolve, rewriting the textbook as it grows older. That's the explosive claim behind variable constants theories, and the evidence might be hiding in light that's traveled across the cosmos for billions of years. Astronomers studying distant quasars, those brilliant beacons powered by supermassive black holes, have noticed something peculiar. The fine structure constant, a number governing how light and matter interact, appears slightly different in galaxies billions of light-years away. It's as if the universe's settings were tweaked in its youth, like a game whose difficulty level shifts mid-play. If true, this would mean the forces we consider fundamental electromagnetism, gravity, even the strength of atoms, might be cosmic habits, not ironclad laws. Here's the kicker: if physics changes over time, the implications are staggering. A slower speed of light in the early universe could explain cosmic mysteries like Horizon Problem, why distant regions of space look so eerily similar. A stronger gravity in the past might rewrite how galaxies formed. Even the vacuum of space itself could have learned to behave differently, like a musician improvising new scales across the ages. But how does a universe learn? Some theorists suggest it's not magic, just nature's way of settling into equilibrium. Picture a vast cosmic algorithm running trillions of variations, pruning what doesn't work until it stumbles upon the stable patterns we see today. In this view, our reality isn't a fixed stage, it's a work in progress, refining its own rules like a sculptor chiseling marble. Now zoom out further. If laws shift across time, could they also vary across space? Imagine patches of the cosmos where gravity repels or light moves in zigzags. Multiverse theories already entertain this idea: countless universes with different physics, most sterile, a few lucky enough to host life. But what if our own universe contains hidden pockets where the rules bend? The answer might lie in a pattern so vast it's been hiding in plain sight: the universe's fractal soul. Zoom in close on a snowflake. Each delicate branch mirrors the whole, repeating in intricate perfection. Now pull back to the cosmic scale, and something astonishing emerges. Galaxies might be arranged in the same infinite, self-replicating dance. This is fractal cosmology, a radical idea that challenges everything we thought we knew about the universe's structure. Forget smooth, evenly distributed matter. Picture instead a cosmos built like a Russian nesting doll, with clusters of galaxies forming patterns that repeat no matter how far you zoom in or out. The implications are staggering. Standard cosmology assumes the universe has an average density, like a well-mixed soup, but if matter clumps in fractal layers, that average doesn't exist. It would mean our maps of the cosmos are fundamentally incomplete, missing hidden tiers of organization. Some astronomers argue this could explain puzzling voids and filaments in galaxy surveys, where matter seems to cluster in ways our models can't predict. Even the cosmic microwave background, the afterglow of the Big Bang, might bear fingerprints of a fractal architecture written in its faint temperature fluctuations. Now here's where it gets surreal. If the universe truly operates this way, it could hint at something deeper. Nature's love of patterns isn't just artistic flair, but a fundamental law. From the branching of trees to the spiral arms of galaxies, the same mathematical rules might govern reality at every scale. That raises a spine-tingling question. Are we living inside a cosmic blueprint where the very large mirrors the very small? But if space is fractal, could it also be pixelated? Just as a digital photo breaks down into tiny squares when you zoom in far enough, some theories suggest space-time itself might have a smallest possible unit, a fundamental grain to reality. Imagine the universe as a cosmic mosaic built from indivisible tiles so tiny, a billion could fit inside a single atom. This isn't sci-fi. Quantum gravity models like loop theory propose exactly that. And if true, it would mean even the void between stars isn't truly smooth, just imperceptibly jagged, like starlight viewed through a microscope. The hunt for these space-time pixels is already underway. Ultra-sensitive experiments are searching for minute fluctuations in light from distant quasars, which might scatter slightly if space has a granular structure. Others are monitoring particle collisions for energy shifts that betray the universe's resolution limit. Finding proof would rewrite physics, not just confirming fractal cosmology, but revealing that reality itself runs on a quantum code deeper than we ever imagined. So the next time you gaze at a frost-ferned window or a galaxy's swirling arms, remember, you might be glimpsing the same cosmic rhythm, echoing from the infinitesimal to the infinite. What if the fabric of space-time isn't a seamless canvas, but more like a glitching video game screen pixelated at the smallest possible level? Beneath the apparent smoothness of reality lies a turbulent quantum foam, where space itself churns with fleeting particles popping in and out of existence. These aren't just random fluctuations, they're the universe's building blocks, flickering so fast we've never caught them directly, yet their fingerprints are everywhere. Take black holes. Their eerie ability to trap information led Stephen Hawking to realize they must have entropy, a measure of chaos. But how does a singularity have entropy? The answer might lie in quantum foam. If space is granular, like a mosaic of tiny tiles at the Planck scale, a distance so small, 1 trillion of them could fit across an atom, then black holes aren't just destroying information, they're scrambling it across spacetime's hidden pixels. Think of it like shredding a document, but at a cosmic level, where every piece is etched onto the foam's seething surface. This pixelation solves another puzzle: why there's a limit to how finely reality can be divided. Just as a digital image blurs when zoomed in too far, the universe might hit a resolution wall, the Planck length. Beyond it, measurements lose meaning, like trying to count the grains in a swirling sandstorm. Some theories even suggest this graininess could warp light from distant quasars, leaving faint distortions in their spectra, subtle evidence we're living inside a cosmic simulation. But here's where it gets wild. If space is pixelated, time might be too. Each frame of reality could tick at the Planck time, a unit so brief, light crosses a Planck length in that blink. That would mean our smooth experience of time is an illusion, stitched together by our brains like a film reel. The universe wouldn't flow, it would refresh, processing itself in quantum clicks. Now shift gears entirely, because antimatter, the universe's elusive twin, might defy gravity in ways that shatter our expectations. If space is a quantum game board, could antimatter be playing by different rules? Most of us think of antimatter as just a quirky twin of normal matter, identical in every way but with opposite charge. But here's the twist: what if antimatter doesn't just mirror matter? What if it defies it? Einstein assumed antimatter would obey gravity's pull like everything else, but recent experiments at CERN are putting that idea to the test by literally dropping antiprotons to see if they fall down. Or if they might do something far stranger. Imagine holding two apples, one made of matter, the other antimatter. Release them, and while the first drops predictably, the second could theoretically rise, repelled by Earth's gravity. If confirmed, this would rewrite one of physics' oldest assumptions, but the implications go far beyond a floating apple. Antimatter behaving this way could solve one of cosmology's biggest headaches: dark energy. If antimatter is gravitationally repulsive, vast clouds of it might have been pushed to the edges of the universe during the Big Bang, forming invisible anti-galaxies that tug against normal matter. This cosmic push could explain why the universe isn't just expanding, it's accelerating. Yet the mystery deepens. Even if antimatter falls upward, where is it all? According to theory, the Big Bang should have created equal parts matter and antimatter. So why does our universe appear overwhelmingly made of matter? One possibility is that antimatter didn't vanish, it's hiding in plain sight, camouflaged as something we've detected but never fully understood. And that brings us to the universe's ultimate ghosts, neutrinos. These nearly massless particles flood the cosmos, passing through planets, and you like they aren't even there. but their eerie properties have physicists wondering, could neutrinos be trespassers from another reality? Some theories suggest they're sterile particles, interacting so weakly with our universe that they might be echoes of a parallel dimension. Others propose they're Majorana particles, a rare breed that are their own antiparticles, blurring the line between matter and antimatter entirely. So while CERN hunts for antigravity, neutrino observatories buried under ice and sea are catching these phantoms in hopes of decoding their secrets. If either experiment delivers, we might not just solve a cosmic riddle, we could crack open a door to realms beyond our own. At this very moment, trillions of invisible particles are streaming through your body, silent cosmic messengers that could hold the key to unlocking parallel dimensions. Neutrinos, nature's ultimate ghosts, are so elusive that a single one could pass through a light year of solid lead without a trace. Yet their very strangeness might be a clue. What if these aren't just ordinary particles, but refugees from a mirror universe brushing against our own? The plot thickens with sterile neutrinos, a hypothetical variant that doesn't just ignore matter, but seems to dance to the rhythm of entirely different physics. Unlike regular neutrinos, which occasionally bump into atoms, these phantoms would interact only through gravity, slipping through our universe like shadows through a wall. Their existence, if proven, would be like finding footprints in snow from someone who was never there. Here's why this rattles the foundations of reality. If sterile neutrinos exist, they might not belong to our universe at all. Some models suggest they're particles from a neighboring dimension, one where the weak nuclear force or even time itself operates differently. Imagine two soap bubbles floating side by side, nearly touching. At their faint boundary, particles could hop between worlds, carrying whispers of a place where everything is eerily familiar yet profoundly alien. The hunt for these interdimensional travelers is already underway. Deep underground, in labs shielded from cosmic noise, scientists are tuning colossal detectors to catch sterile neutrinos' faint gravitational murmurs. Others scour ancient Antarctic ice for anomalies in neutrino behavior that might betray their otherworldly origins. It's detective work on a cosmic scale where every stray signal could rewrite our understanding of existence. But the real shocker, if sterile neutrinos bridge universes, the multiverse might not be some distant abstraction. It could be here, now, woven into the fabric of space like threads in a tapestry we've only just begun to unravel. And that raises a chilling possibility. If particles can cross between worlds, what else might be slipping through? Let's shatter one of our deepest cosmic assumptions, that black holes are purely destructive forces. What if, instead of being cosmic dead ends, they're the birthplaces of entirely new universes? Picture a black hole not as a one-way trap, but as a cosmic womb, where the crushing singularity at its core ignites a new Big Bang. Our universe's accelerating expansion starts to make eerie sense in this scenario because we might not be expanding into anything. We could simply be stretching from the inside of a higher dimensional black hole's event horizon. Think about it like this. If you fell into a black hole in our universe, time and space would warp beyond recognition. But from your perspective, you'd never actually see the singularity. Instead, the extreme curvature of space-time near the core might create an entirely separate, self-contained reality. In this model, the Big Bang wasn't an isolated explosion. It was the moment our universe turned inside out from a parent black hole's collapse. That would make every black hole in our cosmos a potential doorway to another existence, each with its own laws and dimensions. Now, here's where dark matter throws a wrench into the puzzle. If we're living inside an ultra-massive black hole, the mysterious gravitational pull we attribute to dark matter might not come from invisible particles at all. It could be the gravitational echo of a parallel universe bleeding through the event horizon, a shadow reality brushing against ours like ink seeping through paper. Some theories even suggest dark matter is the remnants of a predecessor universe, a cosmic fossil imprinting its gravity onto our own. This idea isn't just wild speculation. The math behind loop quantum gravity, a leading theory uniting relativity and quantum mechanics, predicts that black holes might rebound into white holes, spewing out matter rather than devouring it. If true, our expanding universe could perfectly mirror the behavior of a white hole's explosive output. Even the cosmic microwave background, the oldest light we can observe, might carry subtle imprints of this higher dimensional parent black hole structure. So here's the mind-bending takeaway. Every time a star collapses into a black hole in our universe, it might not be vanishing, it could be birthing an entirely new cosmos. We could be living in one nested layer of an infinite fractal, where universes stack inside universes like Russian dolls. And that raises a haunting question. If our universe was born from a black hole, what cosmic ancestor did it emerge from? Imagine waking up one morning to find the entire world exactly as you left it. Your coffee still warm, your keys still missing except for one impossible detail. Your reflection isn't moving with you. It's reaching for objects you don't touch, reacting to sounds you don't hear. This unsettling thought experiment might be closer to reality than we think. Scientists now speculate that dark matter, the invisible glue holding galaxies together, could be far stranger than mere particles. It might be an entire parallel universe humming along right beside ours with its own physics, its own structures, maybe even its own version of life. Here's the outrageous part. This shadow sector wouldn't just be a faint copy of our world. It could operate by entirely different rules. No electromagnetism, no light, just gravity and hidden forces tugging at the fabric of space from behind a cosmic curtain. Stars made of mirror matter might burn with unknown fuels, while planets forged from these exotic particles could orbit in perfect darkness, the only evidence. Faint gravitational ripples when their matter brushes against ours, like two crowds passing in the fog, unaware of each other's presence, and the anomalies are stacking up. Take galaxy NGC 1052, where stars orbit at speeds that defy visible mass, or the Bullet Cluster, where colliding galaxies left their dark matter halos visibly trailing behind, as if something invisible had inertia. If dark matter were just weakly interacting particles, these quirks might be explainable. But what if it's not particles at all? What if its entire structures, ghost galaxies, shadow black holes, woven from a substance that barely acknowledges our reality? Now here's where quantum entanglement crashes the party. If particles in our universe can instantaneously link across vast distances, could that connection stretch into the shadow sector too? Entanglement might be the universe's way of glitching, briefly revealing threads tying realities together. Some theories suggest dark matter's gravitational nudges could be echoes of entangled particles whispering between dimensions. It's as if the cosmos is a hall of mirrors, and every so often a reflection blinks back. But the real bombshell, if mirror matter exists, it wouldn't just share our space, it might share our time. Parallel doesn't mean separate. These realities could be braided together, evolving in sync but unseen. That means every decision you've made, every star that's died, might have ripple effects in a world you'll never perceive. The universe isn't just bigger than we imagined, it's stranger, layered with secrets waiting in the dark. So the next time you gaze at the night sky, consider this. You might not be looking out into the cosmos. You could be staring into a mirror, and something on the other side might be staring back. Picture two particles born together, then flung to opposite ends of the cosmos. Yet if you tweak one, its partner responds instantly, as if they're whispering secrets faster than light can travel. Einstein famously called this spooky action at a distance, but today quantum entanglement isn't just a laboratory curiosity. It might be the invisible scaffolding holding reality itself together. The early universe could have been a seething quantum network where every particle was entangled in a cosmic game of telephone. As space expanded, these connections didn't vanish. They stretched like cosmic spider silk, subtly influencing how galaxies cluster and spin. Astronomers have even spotted peculiar correlations between distant quasars that align too perfectly to be random. Could these be echoes of the universe's original quantum handshake written in starlight? Now, take this a step further. If entanglement links particles across billions of light years, what does that make the vacuum of space? Far from empty, it crackles with virtual particles popping in and out of existence. A quantum froth some theorists compare to a neural network. The universe might not just contain entangled particles. It could be one vast thinking entanglement, processing information at scales we can barely fathom. Here's where it gets eerie. If the vacuum has structure, even consciousness, does that mean space itself remembers? Experiments suggest quantum systems can retain information about past interactions like cosmic breadcrumbs. Maybe dark energy isn't some mysterious force, but the universe's way of learning from its own entangled history, adjusting its expansion like a breath in the dark. But the real twist, this interconnectedness could rewrite what it means to be separate. You and the star you're gazing at might share quantum threads, remnants of a bond forged at the dawn of time. The night sky isn't just a collection of distant lights, it could be a mirror reflecting back the universe's deepest secret, that nothing is ever truly alone. Picture the void between stars, what we call empty space, as anything but empty. Instead, imagine it as a churning quantum ocean where particles blink in and out of existence so fast they defy measurement. These fleeting guests, known as virtual particles, aren't just cosmic static. They might be the invisible architects of reality itself, shaping everything from the fate of galaxies to the very fabric of time. Here's the twist: even in a perfect vacuum where every atom has been stripped away, this sea of particles never calms. Quantum mechanics insists that space can never truly be empty. It thrums with what physicists call zero-point energy, a baseline hum of activity that even absolute zero temperature can't silence. This isn't just theoretical noise. Calculations suggest the energy in a single coffee cup's worth of pure vacuum could boil Earth's oceans. So why don't we notice it? Because these particles annihilate each other almost instantly, like bubbles bursting in a fizzy drink. Yet their ghostly presence has real consequences. Some researchers believe this quantum foam could be the hidden engine behind dark energy, the mysterious force accelerating the universe's expansion. Think of it like a car running on fumes, except the fumes are the universe's own seething vacuum, pushing space apart from within. Others go further, proposing that virtual particles might carry encoded information, like cosmic flash drives storing data in the fabric of spacetime itself. If true, every cubic inch of nothingness could hold secrets about the universe's past or even its deepest operating code. Now shift perspective entirely. What if this quantum vacuum isn't just background chatter, but the foundation of something far grander? Cutting-edge theories suggest the universe might function like a neural network, an immense self-organizing system where space, time, and matter emerge from interconnected quantum interactions. In this view, black holes could be cosmic nodes processing information. Entanglement resembles synaptic links, and the vacuum's fluctuations act like firing neurons. The cosmos wouldn't just contain complexity. It might be a kind of computation, unfolding in ways we're only beginning to decipher. So the next time you gaze at the night sky, remember, the true marvel isn't just the stars. It's the pulsing, thinking void between them, the silent scriptwriter of reality itself. Imagine the universe not as a collection of inert objects, but as an ever-evolving intelligence, a cosmic brain where stars, galaxies, and even the vacuum of space itself function like neurons firing in an unimaginably vast neural network. This isn't just poetic metaphor. Some physicists argue reality might literally be structured like a learning algorithm, with the laws of physics acting as its training rules. Every particle interaction, every quantum fluctuation, could be part of a self-adjusting system refining its own patterns over billions of years. Think of how artificial neural networks recognize faces or translate languages, not by rigid programming, but by adjusting connections based on feedback. Now scale that up to cosmic proportions. Black holes might serve as dense clusters processing gravitational data, while entangled particles function like synaptic links, exchanging information instantaneously across light years. Even the apparent fine-tuning of physical constants could make sudden sense not as luck, but as the universe gradually learning stable configurations through trial and error. This perspective flips our understanding of mathematics on its head. Equations don't just describe nature, they might reveal the universe's native language. When Newton found gravity followed an inverse square law, or Einstein uncovered spacetime's curvature, they weren't just discovering rules, they could have been glimpsing the cosmic algorithm's source code. Now shift focus to an even wilder implication: time crystals. These bizarre structures, first theorized in 2012 and later created in labs, defy our usual notions of equilibrium. Unlike ordinary crystals with repeating spatial patterns, time crystals oscillate in predictable cycles without energy input, like a perpetual motion machine at the quantum scale. If neural networks sculpt reality, time crystals might be their clockwork, providing the rhythmic pulses that let the universe process information. Picture a galaxy as a kind of cosmic processor, its rotation synchronized with resonances in the quantum vacuum. Or consider that consciousness itself might arise from similar neural dynamics, suggesting universes could, in principle, think in ways we're only beginning to decode. The boundary between physics, computation, and philosophy blurs entirely when reality itself might be the ultimate learning machine. Yet the most tantalizing question remains unanswered. If the universe is computing something, what's the output? The answer could rewrite not just cosmology, but our place within it. Here's the next segment of the script, seamlessly continuing the cosmic journey while diving into the mind-bending world of time crystals. At first glance, time crystals sound like something ripped from a sci-fi novel, structures that don't just exist in space, but pulse in a never-ending dance through time itself. Unlike diamonds or snowflakes with their repeating patterns in 3 dimensions, time crystals are defined by their rhythm. They oscillate in perfect, unchanging cycles without any energy input, like a clock that ticks forever without ever needing to be wound. This isn't just theory. In 2017, researchers at Harvard and the University of Maryland brought these bizarre objects to life in the lab, using chains of ions or nitrogen vacancies in diamonds. When nudged, these systems didn't settle into equilibrium like normal matter. Instead, they locked into a persistent beat, echoing their initial pulse indefinitely. It's as if you plucked a guitar string, and instead of fading, the note rang on forever. Now, imagine time crystals existing naturally in the cosmos, perhaps forged in the extreme conditions of the early universe. Some theorists suggest they could be relics of the Big Bang, frozen remnants of a time when the laws of physics were still settling into place. If true, they'd be more than curiosities. They'd be proof of entirely new phases of matter, ones that ignore the usual rules of entropy and decay. But here's where it gets radical. If time crystals can maintain motion without energy, could they be the key to futuristic tech? Picture quantum computers powered by these self-sustaining cycles, or spacecraft that harness their perpetual rhythms for deep space travel. Even wilder, what if time crystals are already out there, humming silently in the hearts of neutron stars or woven into the fabric of spacetime itself? Their discovery would rewrite our understanding of order, chaos, and the very arrow of time. Yet this leads to an even deeper question. If matter can defy entropy in such a brazen way, what other laws of physics might be illusions? Which brings us to one of the most provocative ideas in modern science. The notion that gravity, the force that shapes galaxies and pins us to Earth, might not be a force at all. We've been taught since childhood that gravity is a fundamental force, an invisible hand sculpting planets and pinning us to the Earth. But what if it's not a force at all? Theoretical physicist Eric Verland throws the rulebook out the window with his radical idea. Gravity might be an illusion emerging from something far stranger, the hidden quantum information woven into space itself. Think of it like heat. A steaming cup of coffee feels warm, but that warmth isn't some separate entity, it's the collective dance of countless molecules. Verland argues gravity works the same way. It's not a standalone force, it's a byproduct of microscopic quantum interactions we can't yet see, like cosmic static shaping the universe from behind the curtains. This changes everything. If gravity emerges from deeper physics, then dark matter, the mysterious glue holding galaxies together, might not be made of undiscovered particles. Instead, it could be a phantom effect, a gravitational echo from the universe's underlying information structure. Imagine walking through a foggy forest and seeing shadows move unnaturally only to realize there's no figure casting them, just patterns in the mist. That's how dark matter might operate, not as invisible stuff, but as a quirk in the cosmic code. The implications would rewrite history. Newton's apple and Einstein's curved spacetime wouldn't be wrong, just incomplete, like describing a rainbow without mentioning light. Even black holes transform under this lens. Their immense gravity might not come from concentrated mass, but from an unfathomable density of information crammed into their cores. Here's where it collides with holographic theory. If gravity emerges from quantum data, and that data is stored on the universe's two-dimensional boundary like a hologram, then the 3D world we perceive could be built from entangled bits in ways we're only beginning to decipher. It's as if the universe runs on a quantum hard drive, and gravity is the operating system glitching in ways we've mistaken for dark matter. Yet the real question remains, if gravity isn't fundamental, what else might be an illusion? The answer could lie in the universe's most elusive act, its habit of erasing its own tracks. There's something unsettling about dark energy, the mysterious force accelerating the universe's expansion. We can't see it, can't touch it, yet it's shaping the fate of everything. But what if we've been looking at it all wrong? What if dark energy isn't some exotic substance, but an emergent property of the universe's own information? That's the bold claim behind holographic dark energy, an idea that ties the cosmos' runaway expansion to the very fabric of reality itself. Picture the universe's edge not as a physical boundary, but as a cosmic hard drive. Every bit of information about what happens inside every star, every atom, every thought, is encoded there like data etched onto a two-dimensional surface. This is the holographic principle in action, but here's the twist. As the universe expands, its surface area grows, and with it, the number of pixels available to store information. Just as stretching a canvas creates more space to paint, cosmic expansion might generate new information capacity at the horizon, and that could be the hidden engine behind dark energy. Think of it like this: when you inflate a balloon, the tension on its surface increases. In the same way, the universe's stretching boundary could create an outward pressure, not from some mysterious fluid, but from the sheer act of encoding more reality into the cosmic ledger. This isn't just poetic imagery. The math suggests that the energy needed to write new data onto the expanding horizon could precisely match the observed strength of dark energy. It's as if the universe is paying its energy bill in information. Now, here's where relativity and quantum mechanics collide. Einstein taught us that space-time bends under mass and energy. Quantum theory insists that information can never be destroyed. Holographic dark energy bridges these ideas, proposing that the universe's accelerating expansion isn't driven by an unknown force, but by the cost of preserving reality's data as space grows. It's not magic, it's cosmic bookkeeping, but if this is true, it flips our understanding of the Big Bang on its head. Maybe the universe didn't explode from a single point, but rebounded from a previous collapse like a cosmic phoenix rising from the ashes. Which raises an electrifying possibility. What if the Big Bang wasn't the beginning, but just the latest bounce in an infinite cycle? What if our universe wasn't born from nothing, but rebounded from the collapse of a previous cosmos? Picture a cosmic phoenix where instead of vanishing into oblivion, a dying universe reaches a critical density and springs back to life in an explosive rebirth. This is the Big Bounce, a radical reimagining of creation that swaps the Big Bang's singularity for an endless cycle of collapse and renewal. The math behind this idea comes from loop quantum gravity, a theory that treats space-time as a woven fabric of tiny, indivisible threads. At extreme densities, these threads don't snap. They stretch like a rubber band, creating a quantum bridge between universes. Think of it like a black hole's singularity, but in reverse. Instead of matter crushing into infinite density, it hits a limit and rebounds, sparking a new expansion. Clues to this cosmic reset might already be hiding in plain sight. Gravitational waves, ripples in space-time from ancient collisions, could carry faint imprints of a pre-bounce universe, like echoes of a scream that never faded. Even the cosmic microwave background, that static hiss from the dawn of time, might bear subtle fingerprints of a prior cycle structure, like shadows of a forgotten world bleeding through. Now shift gears entirely. If universes can recycle, could some stars be made of entirely different ingredients? Dark stars, theoretical objects powered not by nuclear fusion, but by the annihilation of dark matter, might lurk in the cosmic shadows. These bizarre celestial bodies wouldn't glow with visible light. They'd radiate heat as dark matter particles collide and decay at their cores. Their existence would rewrite the stellar rulebook, proving that the universe holds more flavors of fire than we ever imagined. So while telescopes scan the skies for echoes of a bounced cosmos, physicists are rethinking the very nature of matter. The universe might not just be stranger than we thought, it could be stranger than we can think, cycling through lives we're only beginning to trace. Long before the first hydrogen atoms fused into starlight, the cosmos might have flickered to life with an entirely different kind of glow, not from nuclear fires, but from the annihilation of dark matter itself. These hypothetical behemoths, called dark stars, could have been monsters 1,000 times wider than our sun, yet barely visible, radiating only a dull infrared heat as exotic particles collided and obliterated each other in their cores. What makes these shadowy giants so revolutionary? Unlike conventional stars which burn out as their fuel depletes, dark stars could theoretically live forever, feeding on the endless sea of dark matter permeating the universe. Picture a celestial vampire sustained not by blood, but by the invisible matter that outweighs normal stuff 5 to 1. If even one of these primordial relics still drifts in the cosmic deep today, its discovery wouldn't just rewrite astronomy textbooks, it would prove dark matter isn't just a passive spectator, but an active participant in the universe's story. The hunt is already on. Telescopes like the James Webb Space Telescope are scanning the early universe for oddly massive, anomalously cold objects, potential dark stars masquerading as distant galaxies. Even more bizarre, some theories suggest these structures might not be entirely dark after all. As normal matter accumulates around them, they could develop thin, glowing skins of hydrogen like frost forming on a window pane, making them faintly visible at the edge of detection. But here's the cosmic irony. If dark stars birthed the first light, they might also have seeded the first life. Their gentle, steady warmth could have created habitable zones in an otherwise frigid young universe long before ordinary stars ignited. Which raises a staggering possibility. Could life itself be older than we ever imagined? And if life can emerge in such alien environments, what does that mean for its role in shaping the cosmos? Which brings us to an even more profound question. Does life, once it arises, become more than just a passenger in the universe? Could it alter the very fabric of reality? Next topic, life altering the universe. We tend to think of life as a happy accident, a fragile phenomenon that emerged in a lucky corner of an indifferent universe. But what if life isn't just an accidental passenger? What if consciousness itself bends the rules of reality, sculpting the cosmos to become more hospitable over time? This mind-bending idea called biocosmology suggests the universe might not just permit life, it might respond to it. Take the anthropic principle, the simple observation that we exist, therefore the universe must have the right conditions to allow our existence. Some argue this is just circular reasoning. Of course, we find ourselves in a life-friendly universe. We couldn't observe one that wasn't, but biocosmology takes it further. What if observers don't just require fine-tuning? What if they cause it? In quantum mechanics, particles exist in multiple states until observed, collapsing into a single reality. Scale that up, and the universe itself could be a vast quantum system, with conscious beings acting as cosmic observers, locking in life-friendly parameters simply by existing. This isn't just philosophy, it's grounded in the physics of measurement. In quantum experiments, the act of observation literally changes outcomes. Some theorists speculate that, on a grand scale, life's presence could nudge fundamental constants toward stability over billions of years. Imagine a universe where the strength of gravity or the mass of electrons subtly shifts until it clicks into configurations that allow stars, planets, and eventually minds to emerge. It's as if reality is a puzzle solving itself to fit the solver. Now, here's where it gets truly radical. If consciousness shapes physics, could the entire cosmos be the result of a quantum fluctuation? Not the random blip we typically imagine, but one orchestrated by the very observers it spawns. Picture a cosmic game of 20 questions, where the universe's structure is both question and answer, shaped by the act of being perceived. The implications are staggering. We might not just live in the universe, we might be co-creating it. So the next time you gaze at the stars, consider this: the cosmos may not just be a stage for life. It could be a mirror reflecting back the profound truth that to observe the universe is, in some strange way, to complete it. Here's the next segment of the script, crafted to flow seamlessly from the previous discussion while introducing fresh angles and maintaining intrigue. The universe as a quantum mirage deep in the void, where nothingness seems absolute, reality plays a trick. Particles flicker into existence for mere fractions of a second, borrowing energy from the vacuum before vanishing again. These quantum fluctuations aren't just curiosities, they could hold the secret to our universe's origin. What if everything we know, every galaxy, every atom, even time itself, is just an exceptionally lucky ripple in an infinite, silent sea? This is the universe as quantum blip theory, and it's as humbling as it is radical. In the vast emptiness of the quantum vacuum, most fluctuations are tiny and short-lived, but given enough time, and eternity has plenty, an ultra-rare event could occur. A fluctuation so large, so stable, it births an entire cosmos. Our universe might not be special. It could just be the one in a quintillion fluctuation that lasted long enough for stars to ignite, planets to form, and life to wonder about its own existence. But here's the twist. If universes can pop into being randomly, their physical laws might be random too. Most would collapse instantly or lack structure entirely. A handful, by sheer chance, could have just the right parameters for complexity, making our life-friendly cosmos less a miracle and more a statistical inevitability in an infinite multiverse of failures. Now, imagine this cosmic lottery playing out endlessly. Somewhere in the void, another bubble universe might harbor a twisted version of physics, where gravity repels, light crawls, or time runs backward. Others could be stillborn, collapsing before their first star's spark. It's a dizzying thought. We might owe our existence to a quantum dice roll so improbable. It borders on impossible unless you consider that infinity guarantees every possibility, no matter how absurd. Yet this raises a haunting question. If universes are born from chaos, could some share eerie similarities? Could there be a mirror Earth out there, not just in another galaxy, but in another reality? The answer might lie in the quantum shadows, where reflections aren't just possible, but inevitable. A mirror in the void picture a world identical to ours in every way. Same continents, same cities, even the same faces, but with one crucial difference. The laws of physics are inverted like a photographic negative. Particles spin opposite, time flows backward, and matter is replaced by its antimatter twin. This isn't science fiction. The concept of a mirror universe isn't just plausible. It's a theoretical necessity in some interpretations of quantum mechanics. The math behind this is startlingly elegant. To balance the equations governing particle behavior, physicists had to propose the existence of right-handed neutrinos particles that interact so weakly, they might as well belong to another dimension. If these shadow particles exist, they could form the backbone of an entire parallel reality, overlapping ours but forever out of reach, and the clues don't stop there. When NASA Antarctic Impulsive Transient Antenna ANITA detected anomalous particles seemingly rising from Earth's surface, it sparked speculation. Could these be echoes from a mirror universe where gravity pushes instead of pulls? Even the mysterious cold spot in the cosmic microwave background, a vast, inexplicable void in space, has been proposed as a bruise from a collision with another cosmic bubble. But the most tantalizing possibility isn't just that mirror worlds exist, it's that they might not stay separate forever. Quantum entanglement hints that particles can whisper across realities, and if space-time is as malleable as some theories suggest, these mirrors could one day crack open. What waits on the other side? Another us, living another life, or something far stranger? The universe has surprised us before. It's only a matter of time before it does so again. The universe holds a startling secret somewhere out there. A version of you is reading these exact words, but maybe deciding to click away instead. In an infinite cosmos, every possible variation of reality isn't just likely, it's inevitable. Picture this, a planet orbiting a star strikingly similar to our sun, with the same continents, the same cities, even the same faces passing by in crowded streets. On that world, there's another you or something close enough. Maybe they chose a different career, left a decisive conversation unsaid, or took a left turn where you went right. The differences could be razor-thin or vast as oceans, but statistically, in an endless universe, a perfect twin Earth must exist. This isn't fantasy, it's simple probability stretched across infinity. But here's where quantum mechanics throws in a cosmic curveball. Even if an Earth-like world exists, it might not be an exact replica. At the subatomic level, particles make random choices like dice tossed in the void. Over billions of years, those tiny divergences cascade, altering the weather, the rise of civilizations, even the faces in the mirror. A universe where dinosaurs never went extinct. Check one where Rome never fell, almost certainly. The further you zoom in, the more branches appear, like a cosmic game of what if playing out everywhere at once. Now let's take this a step further. If every possible reality unfolds somewhere, could the universe itself be something far more intricate, a vast humming quantum computer? Not just metaphorically, but literally. Some physicists propose that reality might operate like an unfathomably complex algorithm, where every particle interaction, every gravitational pull is a calculation in progress. The twist: instead of silicon chips, the hardware could be woven from the fabric of space-time itself, with black holes acting as processing nodes and entangled particles as data links spanning light years. Think of it this way: a computer doesn't contain information, it is information reshaped in real time. In the same vein, the universe might not just follow physical laws, it could generate them dynamically, adjusting as it computes. That would mean the speed of light, the charge of an electron, even the flow of time aren't fixed. They're outputs of an ongoing cosmic program, one where countless versions of Earth are just different threads running in parallel. So the next time you agonize over a choice, remember somewhere you didn't, and somewhere else you did both. But here's the real question: if the universe is computing all possibilities at once, what's it trying to solve? Here's the next segment of the script, crafted to flow naturally from the previous discussion while introducing fresh insights with a dynamic, engaging tone. Quantum Darwinism, the hidden rules of reality's evolution at the quantum level. The world behaves like an endless buffet of possibilities, particles existing in multiple states at once, timelines branching and merging, probability swirling in a dance of uncertainty. Yet when we look around, our everyday experience feels solid, definite. Why doesn't the universe appear as a blur of overlapping maybes? The answer might lie in quantum Darwinism, an electrifying idea that reality itself evolves, with the most stable states surviving like cosmic winners in a grand selection process. Think of it like this: when a quantum system interacts with its environment, whether through light bouncing off an object or air molecules colliding, countless copies of its information spread outward. Most of these copies are fragile, collapsing instantly, but the most resilient configurations, those that can be observed repeatedly without contradiction, are the ones that stick around. They're classical not because they're special, but because they've outcompeted other possibilities in a kind of information-based survival of the fittest. It's as if reality isn't just there, it's selected through a feedback loop of observation and stability. The speed of light, a cosmic constant or a shifting foundation. Now let's challenge one of physics' most sacred assumptions, the unwavering speed of light. For over a century, Einstein's theory of relativity has treated light's velocity as the universe's ultimate speed limit, a fixed constant written into the fabric of reality. But what if it wasn't always this way? Astronomers studying quasars, distant beacons powered by ravenous black holes, have noticed something peculiar. The fine structure constant, a number that dictates how light interacts with matter, appears subtly different in light that's traveled billions of years to reach us. This could hint that the speed of light itself, or the electric charge of particles, wasn't quite the same in the early universe. Imagine light moving faster in the past, like a cosmic highway with shifting speed limits. This could explain puzzling cosmic quirks, like how regions of space too far apart to ever communicate somehow share identical temperatures. If light traveled faster in the universe's youth, information could have spread further, syncing up the cosmos before physics settled into today's rules. But the real twist: some theories suggest light speed might not even be a fundamental truth. It could emerge from deeper quantum processes, like traffic jams forming from the collective motion of cars. If true, even the most unchanging laws we rely on might just be temporary habits in an evolving universe. And that raises a dizzying question. If light's speed can change, what else might be up for revision? The speed of light mystery. When physics rewrote its own rules, imagine a universe where light didn't always play by today's rules, where photons raced across the cosmos faster in its fiery infancy than they do now. This isn't a thought experiment. Some cosmologists argue that the speed of light might have been variable in the early universe, offering an elegant solution to one of astrophysics' biggest head-scratchers, the horizon problem. Here's the puzzle. No matter which direction we look, the cosmic microwave background, the afterglow of the Big Bang, shows nearly identical temperatures everywhere. But regions on opposite sides of the observable universe were never close enough to exchange heat or information. How did they sync up? If light traveled faster in the past, it could have acted as a cosmic messenger, stitching the infant universe together before inflation kicked in. Think of it like a conductor coordinating an orchestra, ensuring every section hits the same note despite being spread across a vast stage. The temperature connection, a universe in flux, dive deeper and the plot thickens. Certain theories suggest light speed wasn't just faster, it could have been tied to the universe's temperature. Picture a cosmic dial adjusting light's velocity as space cooled, like a car slowing down as the road steepens. In the searing heat of the first moments after the Big Bang, particles and energy would have interacted so violently that light might have zipped through space unimpeded, unbound by today's 186,000 miles per second limit. For Einstein's relativity, this would be nothing short of revolutionary. The constancy of light speed is the bedrock of modern physics, baked into everything from GPS satellites to black hole models. But if early light broke those rules, we'd need a major rewrite, one where relativity becomes a special case in a grander, more flexible framework. A mirror in the dark is another universe staring back. Now shift perspective entirely. If the laws of physics can vary across time, could they also differ across space or even across realities? Enter the mirror universe hypothesis, a parallel cosmos where fundamental constants are flipped, particles spin backward, and time might flow in reverse. The clues are tantalizing. Neutrinos, those ghostly particles that barely interact with matter, seem to wobble between identities in ways that defy simple explanations. Some models propose they're slipping between our universe and a mirror twin, where right-handed versions of these particles dominate. Even gravity might behave differently there, repelling where it attracts here. If true, the mirror universe wouldn't just be a funhouse reflection. It could be a necessity, balancing equations our cosmos can't resolve alone. So while telescopes hunt for echoes of a faster speed of light, particle detectors might soon catch whispers from a shadow reality. The universe, it seems, is still full of surprises, and the next one could rewrite everything we thought we knew. The mirror you'll never meet right now, in some corner of reality, an inverted version of you might be sipping anti-coffee in a city made of antimatter, where time rewinds like a film in reverse, and every left-handed neutrino in our world is right-handed in theirs. This isn't just a fun thought experiment. CPT Symmetry, a cornerstone of quantum physics, suggests such a mirror universe isn't just possible, it might be necessary. Here's how it works. For every particle in our universe, there's an antiparticle with opposite charge and spin. But CPT Symmetry takes this further. It demands that if you flip a particle's charge c, mirror its spatial coordinates p, and reverse time t, the laws of physics should hold true. In other words, a universe where everything is inverted should behave exactly like ours. Now, here's the kicker. Our cosmos overwhelmingly favors matter over antimatter, a mystery that's puzzled physicists for decades. But if a CPT mirror universe exists, the imbalance makes sudden sense. While our realm is matter-dominated, its twin could be antimatter's kingdom, balancing the cosmic scales. It's like two sides of a coin, forever separated but fundamentally linked. Black holes, cosmic supercomputers, but what if black holes, those infamous cosmic vacuum cleaners, aren't just destroyers but processors? Imagine the event horizon as a spherical hard drive, where every particle swallowed adds a bit to the universe's most extreme data storage system. This wild idea comes from the holographic principle, the notion that all the information inside a black hole is somehow encoded on its surface, pixel by pixel. Think of a black hole as nature's most efficient computer. Its singularity crunches matter into oblivion, but the event horizon preserves the information like a cosmic backup drive, just scrambled beyond recognition. Some theorists argue this isn't random. Black holes might be performing calculations using the fabric of space-time itself as circuitry. Even their emissions hawking radiation could be the thermal noise of a universe-scale processor at work. The implications are staggering. If black holes compute what's their output, could the universe be running a simulation we're unknowingly part of? Or are these cosmic behemoths simply executing the universe's source code, one collapsed star at a time? One thing's certain, in a reality where mirror universes and quantum computations collide, the line between science and speculation has never been blurrier. Black holes, nature's ultimate quantum machines. We think of black holes as cosmic trash compactors devouring stars, crushing matter into oblivion. But what if that's only half the story? Beneath their monstrous reputation, black holes might be the most sophisticated computers in existence, running calculations on a scale we can barely fathom. Here's how it works. Every particle that crosses a black hole's event horizon doesn't just vanish, it leaves an imprint on its surface, like data etched onto an unfathomably dense hard drive. This is the holographic principle in action. All the information inside a black hole is somehow painted onto its two-dimensional boundary, encoded in tiny Planck-scale pixels. But it doesn't just sit there. Some theories suggest black holes actively process this data, with their singularities acting like cosmic CPUs performing unimaginably complex operations. So what happens if you fall in? Instead of being shredded into spaghetti, as physics once assumed, you might be translated. Your atoms, your memories, even your consciousness could be digitized into quantum bits, rewritten onto the event horizon's flickering surface. It's as if reality itself has a save function, and black holes are the universe's way of backing up its data. The universe as a frozen symphony now. Shift perspective entirely. If black holes are cosmic computers, could the entire universe operate like an intricate crystal? Not in the way we think of diamonds or quartz, but as a structure vibrating with quantum harmony, where every particle and force resonates in perfect, repeating patterns. This idea, known as the crystalline universe theory, suggests space-time isn't smooth and continuous, but built from discrete, indivisible units like the atomic lattice of a gemstone. Just as sound waves travel through a crystal's rigid structure, light and gravity might ripple across the universe's underlying quantum grid. At the smallest scales, space itself could pulse like a finely tuned instrument, with black holes as dense knots where the fabric warps into something entirely new. The implications are staggering. If space-time is a crystal, it would explain why there's a smallest possible distance, the Planck length, and a shortest measurable time. There's simply no pixel smaller, no way to zoom in further. Even more radical, this crystalline structure might remember distortions, like a diamond storing data in its imperfections. Black holes could be defects in the lattice, places where the cosmic crystal bends so severely, it creates a shortcut to somewhere else entirely. So the next time you gaze at the stars, remember, you're not just looking into the abyss. You might be seeing the glint of a universe built from code and geometry, where black holes compute, space-time sings, and reality itself is far stranger than we ever dared to dream. The universe's hidden grid beneath the swirling chaos of galaxies and quantum particles, reality might be far more orderly than we ever imagined. Picture space-time not as a smooth, continuous fabric, but as an intricate crystal lattice, a geometric grid so unimaginably tiny, trillions of these pixels could fit inside a single atom. This is the radical proposition of crystalline space-time theory, and if true, it would rewrite our understanding of existence itself. Think of it like a digital screen. Zoom out and images appear seamless, but up close you see the pixels. In the same way, the universe might have an invisible scaffolding at the Planck scale, a distance so small, it's a billion times tinier than an atom. Every movement, every collision, even the passage of light could simply be vibrations traveling along this cosmic grid. This would explain some of quantum mechanics' strangest quirks, like why particles can't be squeezed past a certain point. There's simply no smaller to go, just as you can't divide a crystal's lattice infinitely. But here's the real twist. This hidden structure wouldn't just limit size, it could cap energy too. Just as sound waves in a crystal can't vibrate faster than its atomic bonds allow, particles in the universe might hit a fundamental energy ceiling. That could explain why cosmic rays, the most energetic particles we've detected, never exceed a certain threshold. They're not just running out of steam, they're bumping against the universe's built-in resolution limit. Now, shift perspective. If space-time is pixelated, what happens when it stretches? According to general relativity, the universe's expansion should slow over time as gravity pulls everything back together. Yet observations show the opposite. Space is ballooning faster and faster, driven by something we've labeled dark energy. But what if dark energy isn't some exotic force? What if it's an illusion, a side effect of the cosmic lattice itself? Imagine a grid of springs. Stretch them slowly and they resist predictably. Yank them too far, though, and their tension changes. They might snap, warp, or even start pushing back in unexpected ways. Similarly, as the universe expands, its underlying crystalline structure could be generating repulsive pressure, mimicking the effects of dark energy. It's not that space is filled with some mysterious anti-gravity fuel. It's that space itself has a hidden architecture we've only begun to map. This idea turns cosmology on its head. Instead of hunting for dark energy's elusive particles, we might need to decode the universe's quantum blueprints, searching for distortions in starlight or anomalies in gravitational waves that betray the grid's presence. The answers won't just rewrite physics textbooks. They could reveal that chaos was never really chaos at all, just patterns too profound for us to see. Until now, what if dark energy isn't real, just a cosmic trick of the light? For decades, scientists have assumed the universe's accelerating expansion is driven by some mysterious force, dark energy, pushing galaxies apart. But there's a radical alternative. Maybe we're not seeing an actual force at all, just an illusion created by where we happen to be. Imagine standing in the middle of a vast, empty desert. The horizon stretches unnaturally far because there's nothing blocking your view, no mountains, no trees, just miles of flat emptiness. Now, picture our galaxy floating inside a similar cosmic desert, a Hubble bubble, an underdense region of space where matter is unusually sparse. In this scenario, galaxies outside our bubble would appear to rush away faster than expected. Not because space itself is expanding, but because gravity's pull is weaker here. The effect, a perfect mimic of dark energy with no exotic substance required. This idea flips cosmology on its head. Instead of an unknown force stretching the universe, we could simply be sitting in a quiet backwater of the cosmos, misreading the scenery. The evidence, peculiar discrepancies in cosmic expansion measurements. Depending on where we look towards certain supernova or distant quasars, the rate of expansion doesn't always match up perfectly. If we're inside a giant void, those inconsistencies start making sense. But here's the catch. This void would need to be enormous billions of light years across, and statistically unlikely. Unless, of course, the universe itself isn't what we think. A twist in the cosmic plot. Is the universe a loop? Now, let's take it further. If dark energy might be a mirage, what about the shape of space itself? Forget the classic idea of an infinite, flat universe. What if the cosmos is closed, a vast, hyperdimensional loop where traveling far enough in one direction eventually brings you back where you started? It sounds like science fiction, but the math doesn't rule it out. Evidence might already be hiding in the cosmic microwave background, the faint glow of the Big Bang. Some analyses suggest subtle anomalies in this radiation, patterns that could hint at a universe with positive curvature, like the surface of a sphere. A closed universe wouldn't just redefine our sense of scale, it could rewrite the fate of everything. Instead of expanding forever into cold, empty darkness, space might eventually collapse back on itself in a big crunch, or even cycle into a new cosmic epoch. The implications are staggering. If the universe loops, then every line of sight eventually curves back to its origin. Galaxies at the edge of our observable universe might just be the light from our own local neighborhood, stretched and bent after traveling the cosmic loop for billions of years. Suddenly, dark energy's illusion and the universe's shape become two pieces of the same puzzle, one where perception and reality blur in ways we're only beginning to grasp. So the next time you hear about dark energy, ask yourself, are we witnessing a fundamental force of nature or just an accident of cosmic geography? The answer might be stranger than we ever imagined. A twist in time's arrow. When the future echoes backwards, Einstein's equations hold a secret buried in the math of paths called closed time-like curves, where space-time bends so severely that time itself loops back like a Möbius strip. Picture a cosmic treadmill. Take one step forward, and you might find yourself right where you started, only earlier. This isn't just theoretical whimsy. Wormholes, certain black hole geometries, and even hypothetical cosmic strings could warp time into these paradoxical circuits. But here's the catch. If time can loop, why haven't we met time travelers or stumbled into paradoxes? Quantum mechanics might hold the answer. At the subatomic level, particles behave in ways that seem to self-correct against inconsistencies. Some models suggest quantum effects would act like cosmic editors, tweaking probabilities to prevent paradoxes before they happen. Imagine tossing a rock into a pond, only for the ripples to reverse course and cancel the splash before it occurs. The universe might work similarly, ensuring that any event threatening causality gets quietly rewritten behind the scenes. What's truly staggering is the implication. If closed time-like curves exist, causality isn't a one-way street. The future could ripple backward, subtly shaping the past. Ancient stellar explosions might carry echoes of events yet to come, or human choices today could be nudged by consequences decades ahead. It's as if time isn't a river flowing in one direction, but a hall of mirrors where reflections bend and blur. Yet the grandest question remains, if time is this malleable, how do we know anything is fundamental? Which leads us to an even more radical possibility, that the universe itself isn't the base layer of reality, but an intricate simulation running on some unfathomable cosmic hardware. The universe as cosmic code. Are we living in a simulation? The idea that reality might be an artificial construct isn't new. Philosophers have toyed with it for millennia. But today, physicists approach it with equations. If the cosmos operates with mathematical precision, could it be because it's literally built from math? Some theories propose that space-time behaves like a lattice of information, with particles and forces emerging from underlying computational rules, like pixels lighting up on a screen. Clues might lurk in the fabric of reality itself. Ever notice how light comes in discrete packets, photons, or how quantum particles snap between states like a buffering video? These granularities could hint at a universe running on finite processing power. Even the speed of light might not be a physical limit, just the processor's clock speed, ensuring the simulation doesn't overload. But the real test lies in gravity. At tiny scales, spacetime should fizz with quantum foam, a seething turbulence that high-energy particles could interact with. If detectors ever spot anomalies in particle collisions, like energy leaking into unrendered dimensions, it might suggest our universe has a resolution limit. Like a character in a game realizing the walls are just 2D textures, we could find cracks in the cosmic code. Of course, not everyone buys the simulation hypothesis. Critics argue it's unfalsifiable, a slick metaphor masquerading as science. Yet the debate itself reshapes how we see reality. Whether the universe is a simulation or not, asking the question reveals something profound. Existence is far stranger and far more structured than we ever imagined. And that's a truth no algorithm can diminish. The simulation hypothesis: are we living in a programmed reality? Picture this: every star, every atom, even your own thoughts might not be fundamental, just lines of code in an unfathomably advanced simulation. This isn't the plot of a sci-fi movie. It's the simulation argument, a serious hypothesis debated by physicists and philosophers alike. The logic is startlingly simple. If any civilization ever reaches the technological capability to create hyper-realistic universe simulations, the number of simulated realities would vastly outnumber the original one. Statistically speaking, the odds that we're living in the base layer of existence almost vanishingly small. But here's the catch: this isn't proof, just a numbers game. To move beyond speculation, we'd need to find something like a cosmic glitch, a telltale sign that reality has seams. Some researchers point to quantum mechanics as the first clue. Why do particles exist in fuzzy, undefined states until observed? Could that be the simulation's way of conserving processing power, only rendering reality when someone's looking? It's as if the universe runs on an optimization algorithm, loading details on demand, like a video game reducing resolution in unseen areas. Then there's the infamous Planck length, the smallest possible unit of space. No matter how hard we try, we can't probe anything smaller, almost as if we're bumping against the universe's pixel limit. Even the speed of light might not be a physical barrier, but a built-in safeguard to prevent the simulation from overloading. Imagine a computer overheating. If too much data is processed at once, our cosmic speed limit could be a failsafe. But the real kicker: whether we're in a simulation or not, the implications are identical. Reality, as we know it, operates with mathematical precision, bending to rules that feel designed. Does that mean some higher intelligence wrote the code? Maybe, or perhaps the universe is simply structured in a way that mirrors computation, blurring the line between physics and programming. So here's the ultimate question: does it matter? If this is all a simulation, it doesn't make your joys, struggles, or curiosity any less real. After all, even if existence is just an algorithm, it's one complex enough to ponder itself. And that might be the most astonishing glitch of all: a cosmic farewell, where wonder meets discovery after venturing through holographic dimensions, conscious universes, and time-bending paradoxes. One truth becomes achingly clear: reality is far stranger than our boldest dreams. These theories don't just challenge textbooks, they shatter the boundaries of what we thought was possible, revealing a cosmos that's alive with mystery. And while we may not yet have definitive answers, that's the beauty of science. Every question unraveled leads to a dozen more, each more thrilling than the last. Think of cosmology as an endless frontier where today's wildest what-if could be tomorrow's groundbreaking discovery. The holographic principle, quantum consciousness, even simulated realities. They weren't born from fantasy, but from meticulous math and daring imagination. That's the heart of scientific progress, the courage to stare into the unknown and whisper, "What else?" So where does this leave us? Not with tidy conclusions, but with something far more valuable, a deeper curiosity. Whether the universe is a cosmic computation, a hologram, or something beyond our current vocabulary, one thing's certain: we're part of a story still being written. And that's exhilarating. If this journey through the cosmos' wildest ideas sparked your sense of wonder, don't let it end here. Tap that like button if your brain's still buzzing. Subscribe to keep exploring the universe's deepest secrets, and drop your most mind-bending theory in the comments. After all, the next revolutionary idea might just come from you. Until then, keep looking up and never stop questioning. The universe rewards the curious. End screen, call to action visuals, suggested videos, and a final cosmic backdrop fading to black.